Hello, guys, and welcome to chapter 8C, in which we are looking at differentiation 3. In this particular lesson, we are going to cover implicit differentiation, parametric differentiation. We will look at increasing and decreasing functions, turning points, second derivatives, gradients of tangents and normals, and applications of curve sketching. Please don't forget to subscribe to this channel and watch this video detailedly to the end. You can equally visit our blog where you can have the PDF of this particular lesson, GCE Math Panel online classes, or you can go to www.gcemathpanel.blogspot.com where you will have information about all of our material. Stay tuned. So we begin by implicit differentiation. For most functions, which we have seen so far, they have been expressed in explicit form. That is, they have been expressed in a very simple form, in which most of those cases we just have y being a function of x, with y being on the left-hand side alone, and all the terms in x on the right-hand side. Those have been explicit functions. Now we are going to look at implicit functions in which the function is expressed in terms of x and y. For example, here we have xy equals 1. So this is some sort of an implicit function. You can actually arrange it to look like an explicit function, but we note that implicit functions look like this. All right, let's keep all the grammar and move to solving. So let us start by differentiating this first function, which we have x squared plus y squared is equal to 25. Normally, this is the equation of a curve. And let us see how we differentiate this. This is an implicit function. So we differentiate x squared with respect to x. We will have 2x. We now differentiate y with respect to x. We are going to have 2y dy dx. So note that since y is a function of x, when we differentiate y, we will be left at the end with dy dx. So this is equal to, when we differentiate the constants, what do we have? We have 0. So from here, we can make dy dx the subject of the formula because we are looking for dy dx. And dy on the x will be equal to, so if you carry 2x, the right-hand side becomes minus 2x. And we divide that by y, right? So we have minus 2x divided by y, by 2y's. Normally, the 2's will cancel out, and you'll be left with minus x on y. So this is what we have. But a question like this may equally be asked, and they say that you should leave your answer only in terms of x. So if I'm to leave this only in terms of x, then my dy dx or y prime will be equal to, the numerator is already in terms of x, so I have minus x. And for the denominator, I have to make y the subject of the formula from the equation. So if I have to make y the subject of the formula from the equation here, I will have y squared to be equal to 25 minus x squared. And then I get the square root of all of that. So we have 25 minus x squared. Now we take the roots, right? So this will give us the square roots of all of this. And we have expressed this function in terms of x only. All right, let's look at the second example, still on implicit differentiation. All right, so we have find y prime in this and also find y prime prime. Note that y prime prime is the second derivative of this curve. So let us start with y prime. So differentiating this implicitly, we will have 3x squared plus 3y squared dy dx to be equal to, when you differentiate the right hand side is a constant, you are going to have 0, right? 0. So now at this point, we can make dy dx the subject. This will give us dy dx to be equal to minus 3x squared. So minus 3x squared divided by what? Over 3y squared. So, but we can cancel out the 3's, right? And we'll be left with minus x squared on y squared. So this is the first derivative, but according to this question, they want us to also look for the second derivative. So we have to differentiate again to have the second derivative. So the second derivative, which you can call y prime prime, or d squared y over d x squared, will be equal to, so I differentiate this function again. And here I'm going to apply the rule that we call the quotient rule. The quotient, because this function is a quotient, a fraction. Since the quotient, if you look at lesson 8b, we have the quotient rule there. This is lesson 8c, or differentiation 3. So this will give us, we keep the bottom constant, y squared. We differentiate the top, we have minus 2x minus the bottom now constant, now minus the top constant, minus x squared. We differentiate the bottom. When you differentiate the bottom, what are we going to have? We will have 2y dy on the x. Remember that we are differentiating y with respect to x. All this on the bottom squared. So what is the bottom here? The bottom is y squared, right? So we have y squared all raised again to the power 2. So this will be equal to minus 2x y squared plus 2x squared y, but we know the value of dy dx, right? From this first part of the function, dy dx is negative x squared on y squared. So all this on y to the power 4. So when we simplify this, we are actually going to get the second derivative of this function. That is giving us minus 2x y squared plus 2x to the power 4. Now, because of this negative sign here, we are going to have minus at that point. So now this one becomes minus. So we have now minus 2x to the power 4. This y will cancel out to this y here, and we'll be left with on y. So all this on y. So divided by the denominator that we have this function by y to the power 4. So we can further simplify to have the results. So You simplify this and you obtain the complete result. That is y prime. That's the essence. Okay. Okay. So normally, if I am to work further to get the final answer, because I know you are eager to get the final answer too, then that should give us, let me write it this way. That should be equal to minus 2x y to the power 3 minus 2x to the power 4 so divided by y to the power 5. Divided by y to the power 5. Okay, so that is first and second derivative. If there's any issue and error, I think you can actually adjust. And that is it. Let's move to the next example. Now we have find y prime and sine x plus y is equal to y squared cos x. And this is also another implicit function which we are going to differentiate. And you have to take care with this one so that we don't make a mistake. So here, when you differentiate this core, the core of this sine function, look at it. This core is another function. So to differentiate the sign of this function, we will say we differentiate this core. When we differentiate x plus y, what are we going to have? We are going to have 1 plus dy dx we will now differentiate sine x. What are we going to have? So when we now differentiate sine x plus y, we are going to have cos x plus y and this should be equal to, or you can decide and use the chain rule here, you have the same result, okay? Now, this function on the right-hand side is a product of two functions. So we keep the first function constant. We differentiate the second, we'll have negative sine x, right? So we'll have negative sine x, then put the negative in front here. Now, plus the second function, now constant. I will differentiate the first. So we'll have 2y. 2y, do we end there? No, we have 2y dy on dx. So now we are supposed to bring like terms together. Like terms together. So if I expand the left-hand side, I'll have cos x plus y plus cos x plus y dy dx and on the right hand side this will be equal to minus y squared sine x plus 2y cos x dy dx. So to make dy dx the subject of the formula, I'll bring this one to the left hand side. while we move this to the right-hand side. So on the left-hand side, we'll be left with cos x plus y cos x plus y minus 2y cos x so we are factorizing, right? All of this times dy dx will be equal to what we have on the right-hand side. So this will be equal to, so on the right-hand side, we are going to have minus y squared sine x minus cos x plus y divided by, so when you have this, we now divide both sides by this cos x plus y minus 2y cos x. So if you divide both sides, we are going to have cos x plus y cos x plus y minus 2y cos x such that this one is going to disappear on the left-hand side, right? So we no more have this on the left-hand side. So this is the derivative that we obtain, okay? So this is the derivative of this function. All right, this was a good example. Let us move on to the next item. Let's move on to the next item. Okay, so we have this other curve here now to find y prime in this function and the gradient when x is equal to 1. To find y prime, to find this gradient when x is equal to 1. So for this particular question, you can have this is actually another example of an implicit function. So we are going to have, to differentiate this, we'll have minus 3. So let us put this one in brackets now. So minus 3, we have this function xy. We have this function xy. Let us differentiate. We'll keep the first function constant, x. We differentiate y, we have y prime. Let me use prime here now. I'll make this line longer to show that it's prime. Plus, we now keep y constant and differentiate x. We'll have 1. We now differentiate x squared. We'll have 2x. This should be equal to, when you differentiate 11, we are going to have 0. So when we open out these brackets, we are going to have minus 3x y prime minus 3y's plus 2x is equal to 0. And from here, our y prime will be equal to 3y's minus 2x, all this on minus 3x. Now they want us to find this gradient at the point where x is equal to 0. I'm sorry, when x is equal to 1. But according to this function, when x is equal to 1, what do we obtain? So when x equals 1, let us see, we have to use the equation. When x equals 1, we want to obtain the value of y. Because you cannot look for y of 1 without obtaining the value of y. So when x equals 1, y will be equal to So if you substitute 1 in all of this equation up, in the given question, what are we going to have? We will have minus 3y plus x, the x is 1, so plus 1 is equal to 11. And from that point, we'll have y to be equal to 10 on 3. We have 10 on 3. So we have our y to be equal to, so this implies y is equal to 10 on 3, which is minus. So from here now we can look for y prime of 1, that is when x is equal to 1. So this will be equal to 3 into y is minus 10 on 3, minus 2 into x is 1, all this on minus 3 into 1. So this will give us minus 10 minus 2, minus 12 divided by minus 3, and this will be equal to 4. So y prime of 1 is equal to 4. So that's the gradient of this curve at the point where x is equal to 1. Okay. All right. Let's go on. The next part of the questions. All right, you can equally do this one. Find y prime in sine x minus cos y equals 2x at x equals 0. So you can do this differentiation very fast. This is also an implicit function. So we differentiate sine x, we'll have cos x. We're going to have cos x. Okay. Okay, let me go back to the equation. Right, this is the equation. So we'll have cos x minus, so when we differentiate cos y, we have minus cos x. So minus minus, this will give us plus. When we differentiate cos y, we have sine y dy dx, includes y prime, should be equal to, when you differentiate 2x with respect to x, we have 2. So this implies here that y prime will be equal to 2 minus cos x all this on sine y. Sine y. Now, in this equation, when x is equal to 0, we need to look for the value of y, right? So when x is equal to 0, we will have sine 0 is 0 minus cos y. Want to look for y is equal to 2 times 0, 0. So we have cos y to be equal to 0. When is the cosine equal to 0? So if cos y is equal to 0, then this implies that y should be equal to 90 degrees, because no cos 90 is 0, right? or we can use pi on 2. So y is equal to pi on 2. Pi on 2. So it therefore means y prime of 0 will be equal to, because at that point where x is equal to 0, it will be 2 minus cos 0, all this on sine y, sine pi on 2, sine pi on 2. And this will give us cos 0 is 1. So 2 minus 1 is 1 over sine pi on 2, that's sine 90 is 1. So this gradient is going to be equal to 1. So we have 1 for that. Right. So this is the last example. Now let us look at parametric differentiation. Parametric differentiation. All right. All right. So this question is on parametric differentiation. These are a special question with chain rule with 3 variables. So they want us here to find the y, the x. Now let's just look at this example. With this example, dy on dx will be equal to dy on du. You can see this function relating to this one, right? Times, the next one should be a function of u now. Du on, the next function is t, u and t, on dt times, function with t and x now, times dt on dx. So from here, we can get dy du. When you differentiate this one with respect to u, you are going to have cos u times, now du dt. When you differentiate the ln t, you have 1 over t times 1 over t times dt dx now. Dt dx will be equal to 2. So at the end, we are going to have 2 over t cos u, but we know that u is equal to ln t. So we have the cosine of ln t. So you have expressed everything in terms of t. This is our dy dx, okay? Yes, so from here we can replace these parameters and give everything in terms of x if you want to. Okay, let us look at the next part. We're now looking at parametric differentiation. So what happens when the function is given as parameters? That means, for example, x is a function of t and y is a function of t. Like we have just seen in this previous example that I have applied chain rule. So what do we do for parametric differentiation? Let's look at this example. If x is equal to sine t and y is equal to cos t, find dy dx. So for parametric differentiation, we will have to look for dx dt. And what is dx dt? So dx on dt is equal to cos t. And what is dy dt? Dy dt on dt is equal to negative sine t. So from here, what will be dy dx? Dy on dx will be equal to dy on dt all of that divided by dt dx. All of that divided by dx, divided by dx dt. All of that divided by dx dt. This can also be written as dy on dt times dt on dx. So according to this equation, our answer is going to be equal to dy dt. What is dy dt? Is negative sine t divided by dx dt is cos t. So this will finally give us negative tan t. Since sine t on cos t is equal to tan t. So that gives us tan t. Well, another way to answer the same question is, if you look, you see that you have x is equal to sine t and y is equal to cos t, right? So you can transform this curve. We know that sine squared t plus cos squared t is equal to 1. Sine squared t plus cos squared t is equal to 1. So that implies we will have sine squared t is the same as x squared, according to this question, plus cos squared t is the same as y squared, according to this question. That should be equal to 1. And we can now do parametric implicit differentiation. This will give us 2x plus 2y y prime is equal to 0. And from here, y prime will be equal to minus x on y, where our x is equal to sine t, which is the same thing that we have here, and our y is equal to cos t. So you're going to have the same answer. Okay? So there are two methods that this question can be answered. You can either use the first method or use the second one. Right, next question. Next question. Given that x is equal to 2 sine t and y is equal to cos t, find dy dx. So this one can equally be answered in two ways. Right. Yep. So here, let us look for dy dx dt. So dx on dt will be equal to 2 cos t. And dy dt will be equal to minus sine t. Now from here we can have our dy dx on the x to be equal to, that will just be equal to dy dt divided by dx dt. So we'll have minus sine t divided by what? 2 cos t. And the result of this will be equal to minus a half tan t. Now, another way to answer this question is to transform this curve. So from this point, you see that our sine t will be equal to x on 2. And we know that sine squared t plus cos squared t is equal to 1. From here, sine t will be equal to x on 2. So we have x on 2 squared plus our cos t is y plus y squared is equal to 1. And we can differentiate this implicitly. To differentiate this, we'll have 2 times x on 2 to the power 2 minus 1. That will just be x on 2. We now differentiate the core. We are going to have a half plus 2y dy, so 2y y prime is equal to 0. So these two cancel out these two, and we'll be left with y prime to be equal to minus x on 2 divided by 2y, which is the same as minus x on 4y. But you know that our x is equal to 2 sine t. So we have minus 2 sine t divided by 4 cos t. So when we cancel this out, 2 cancel out the 2, we left with a minus a half, 2 here 1, 2 here 2 times. So we have minus a half tan t. So we still have the same result, right? Yes, so we have the same results. You can use any of these methods, but be careful with the second one because some students will forget to differentiate the core and they will not obtain the value of this a half here. Yes, many students will forget. Be careful. Okay, let's take another example. Example 3, right? So given that t is equal to x is equal to t plus 3 and y is equal to t squared plus 1, find dy dx and the slope of the tangent at t equals 2. So dy dx, let us call this, we can use x prime. So what is x prime? X prime is dx dt, okay? X prime is equal to 1. And what is y prime? All right, let me use the prime in this way. So with respect to t. So y prime be equal to 2t. And from here, y prime itself, that is dy dx, will be equal to dy dt over dx dt, which is equal to 2t. And what will be the slope of this curve at t equal to? So you are looking for y prime of 2. This will be equal to 2 times 2, which is equal to 4. Right. That's it with this question. Next question. We have x is equal to 3 plus 4 cos t and y is equal to 1 minus sin t. Find the y, the x, and the slope of the tangent at pi on 4. At pi on 4. Okay. So here the x dt will be equal to, or you can make cos t and sin t the subject of the formula, and sin squared t plus cos squared t is equal to 1, and do the same thing, all right, like we have done in the previous examples. So here the x dt will be equal to minus 4 sin t and dy dt will be equal to minus cos t and therefore y prime will be equal to dy dt, which is minus cos t divided by dx dt. So our minus 4 sin t, the minus signs will cancel out. So this will give us 1 over 4 cot t. Okay. And what will be the gradients of the tangents at pi on 4? So we're looking for y prime of pi on 4, where t is equal to pi on 4. This will be equal to 1 over 4 into, what is cot pi on 4? Cot pi on 4 is sin pi, it's cos pi on 4 and sin pi on 4. But we know that sin pi on 4 is equal to cos pi on 4, which is root 2 on 2. So this gives us 1. So this gradient of the tangent is 1 on 4. The gradient of the tangent is 1/4. Right, next example. Next thing. Okay. Now we have the other curve as well. So you can look for dy dx here when x is equal to 0. This one is also very simple. Let's just scratch it very fast. So let me call this one x dx dt. This will be equal to 1. And dy dt will be equal to 2 t squared plus t times the derivative of the core times 2t plus 1. So this is what we have. Now we say find the value of t when dydx is equal to 0. So when this is equal to 0, you can find the value of t. So in this case, it implies that either t squared plus t equals 0 or 2t plus 1 equals 0. So we have t squared plus t equals 0 or 2t plus 1 is equal to 0. So this first one, we will have t into t plus 1 equals 0. And from here, either t will be equal to 0 or t is equal to minus 1. Now this other second one, we'll have t to equal to minus a half. So these are the three values of t. We have 0, minus 1, and minus a half. So these are the values of t when dydx is equal to 0. All right, next things. So given that given t minus 1 and y equals t is the t, find y prime and y prime prime. Find also y prime of 1 and y prime prime of 0. That's another good question, right? So we have dx dt is equal to 1. Is equal to 1. And dy over dt is equal to, we have to apply the product rule here because this is a function and this is another function. We keep the first function constant, we differentiate the second, plus the second constant, we differentiate the first. Differentiate the first, we just have t. So this is this function when it differentiates. So from here, our dy dx will be equal to dy dt divided by dx dt. So that will just give us t e to the t, or let me factorize it. That's going to give us a t plus 1 e to the t. Now we can equally look for y prime prime. I'm to differentiate this one again. So we differentiate, we'll have y prime prime to be equal to, we keep the first function constant. We differentiate the second. Note that when you differentiate e to the t, it's the same thing, e to the t, plus we keep the second constant. We differentiate the first. So what will be the end result here? We have t plus 2 e to the t. Now we have to look for y prime of y. So y prime of 1 will be equal to, this is our y prime now. This y prime is dy dx. So when t is equal to 1, what are we going to have? We'll have 1 plus 1, 2 e, because this is the power 1. And what will be y prime prime of 0? So when t is equal to 0, we will have, when t is equal to 0, we are going to have, with the second function, we have 2 times e to the power 0. So that will just give us 2. So if you fit 0 in the second one here, this is y prime prime. You have 0 plus 2 is 2. E to the power 0 is 1. So 2 times 1 is 2. That's why we have this. So this is a similar one which you can equally do. You can do this one as assignments. Please do this one and send to the WhatsApp group. Let us check, or leave your answer in the link below. It's an assignment, homework for you. Just the same like the other one, right? Yeah. You know that when you differentiate in t, the y dy over dt here is equal to the derivative of this core, which is 1, over the function itself over t. So dy dt is equal to 1 over t. So I hope you can look for y prime of 1, y prime prime, and y prime prime of 0. Okay. The next thing we'll be looking at is increasing and decreasing function. We also discuss this as the monotonicity of a function. All right, you'll watch the next video and you're going to see that there.